Welcome. Today we continue 3.7, the chain rule. We are in day 2, and we will look at a little more theory and practice. The chain rule, day 2, theory and some more practice. So first of all, the more practice. Recall some basic derivative rules, that the derivative of square root of x is 1 over twice the square root of x. The derivative of 1 over x is negative 1 over x squared. See if you can use those rules to help you with the chain rule for the first 2 problems, and then take a look at the other problems as well. Pause the video, give these things an honest try, and when you are ready to check your work, play the video again. All right, let's take a look. I will reveal the answers one by one, so pause and check if you want, and make sure that you did all right. Okay, let's talk about a different way of thinking about the chain rule. This is the Leibniz form of the chain rule. Suppose that y depends on u, and u depends on x. For example, maybe y equals the sine of u, and u is x cubed. So y is a variable that depends on u. As u changes, that's going to change the value of y, and u depends on x. So as x changes the value of u. What we really have here is a chain of dependencies. Y depends on u, and u depends on x. dy over du, what that means is, how much does y change relative to u? So if this is 2, if dy du is 2, that means that y is changing twice as much as u changes. If u changes a little bit, then y is going to change twice as much. If dy du is negative 2, well, that means that if u changes a little bit, y changes twice as much in the opposite direction. Similarly, we have du dx. du dx says, how much does u change relative to x? Our goal is to figure out dy dx. Y is a function of x. How do we find dy dx? Let's take the chain from the very top to the bottom. Y is a function of x. What is dy dx? So can I figure out dy dx based on dy du and du dx? And the answer is yes. Yes, I can. The answer is that dy dx, going from the very top to the bottom of the chain, is dy du times du dx. I have an animation I want to show that kind of helps make this idea clear and why this is the correct formula. Here's the animation. Imagine an X wheel. The wheel is turning by some motor. The motor makes the X wheel turn, and there's a U wheel and there's a Y wheel. And the thing about these wheels, first of all, I can change their radii. I can make them bigger and smaller. But the big thing about these wheels is that I can connect them. So if I connect the X wheel and the U wheel, now the X wheel is driving the U wheel. And it turns out that since the radius of the X wheel is 4 times bigger than the radius of the U wheel, then one turn on the X wheel will force 4 turns on the U wheel. We might say that du dx is 4. U is turning 4 times faster than X. For every little bit of change in U, X changes 4 times that much. This is kind of fun too. I can also cross the belt. So how about this? Now, U is spinning 4 times as fast as X, but it's spinning in the opposite direction. So we might say that du dx is negative 4. So 4 times as fast in the opposite direction. Let me put the belt back to normal. So the X wheel is driving the U wheel. Let's connect U with Y. Now the U wheel, the X wheel drives the U wheel, and the U wheel drives the Y wheel. But Y is twice as big, the radius is twice as big as U, so dy du is half. For every change in U, Y changes half as much. Let's cross this belt. And so now, The big question is, what is this relationship between x and y? For every change in x, how much does y change? And maybe you can see it. It is -2. Can you see as the x goes around once, y goes around twice in the opposite direction? And it seems reasonable in this physical setup that the product is appropriate. So x drives u is going 4 times as fast. U drives the y is going half as fast in the opposite direction. And so the product of those two, 4 times -1/2, is -2. So this is an intuitive justification for this chain rule. All right, so let's see how we actually use this idea in computation. Example, suppose y equals sine of u and u equals x cubed. Compute dy dx. So here's our formula, the Leibniz form of the chain rule, dy dx equals dy du times du dx. Let's just take each function individually and take its derivative. The derivative of y with respect to u, where u is the variable, that's just simply cosine u. And the derivative of u with respect to x is just 3x squared. But now my answer has a mix of variables. It has both u and x. I don't really want that. Ultimately, I just want only variable x to appear. So I do one more step, and I replace that u with the x cubed, because after all, that's what u really is. And there we have it. We have our final solution, all in terms of x. Your turn. Take a look at these 3 problems. Try your best. See if you can follow the example from the previous slide, and use the Leibniz form to compute the derivative in each case. All right, pause the video and give it a try. And here are the solutions. Number 1, number 2. Check your work. I hope you did well. Number 3. How to go. All right, so make sure you're really understanding this. Check your work. Don't cheat. Give this an honest try, and make sure that you can work out any discrepancies that you might see between what's on the screen and what's on your paper. Last idea. Getting the formula f prime of g of x times g prime of x. How does our Leibniz form, remember the Leibniz says dy dx equals dy du times du dx. How in the world are these two things related? How can I justify one formula based off the other? And here's the idea. Let's suppose that y equals f of u, so y is the outer function. I sort of have f of g of x, so it's almost like u is my g of x. Oh, and there u is g of x. So if y is a function of u and u is a function of x, let's compute dy dx. So the Leibniz form. And what is dy du really? Dy du is just f prime of u. Du dx is just g prime of x. F prime of u, let's do the substitution. That's f prime of g of x times g prime of x. And hey, look at that. It's the original chain rule. So we use the Leibniz form to justify why the chain rule works. This kind of multiplication seems reasonable, and I didn't actually prove it. I'm waving my hands a little bit. The proof is actually much more detailed and more in-depth than I really want to go. But from our discussion, from the wheels example, maybe this product seems reasonable at any rate. So using the Leibniz form of the chain rule, then we can justify the original chain rule that we had. In truth, for actual calculations, I personally find our original formulation of the chain rule easier to work with if we can just remember that formula. In this video, you got some more practice. We looked at the Leibniz form and we saw a different way of doing the chain rule, and this is a good place to stop.